Today, we're going to be discussing a follow-up analysis of Bedson et al.'s 2019 paper on community engagement during the 2014-16 Ebola outbreak in Sierra Leone. Here, we present methods for cleaning the text and analyzing the original text data, methods for joining road networks and time series plots with geospatial components, and methods for evaluating policies at the chiefdom level and predicting outcomes. We started by replicating Bedson et al.'s original analysis of interview volume during the initial triggering events and the follow-up events. Here we can see below the two time series plotted next to each other. We're also curious about the underlying data integrity at each time step. Looking at the text responses, we can see that there are thousands of instances where multiple columns have been exactly repeated across survey responses. Moving to a weekly aggregation of responses, here we see in orange cases where there were more than two duplicates across text response columns. We can see that earlier on in the survey and when survey volume was higher, there were more duplicates in the text responses. These are often from the same chiefdom or as very closely spaced together when we looked at the duplicates temporal distribution within the data. From there, we looked at correcting text errors in the form of spelling errors. And to do this, we used a package in Python called SimSpell. And this uses edit distance and frequency tables to select correct words when a spelling error is detected. And the default performance is presented in red here. So we observed a misspelling of Ebola as Ibala, which was corrected to Bala. This is obviously not the behavior we'd like to see. So we take the distribution of all words in the text responses from the Ebola dataset, and we compare them with the SimSpell frequency table, and we can see the distributions are about as you'd expect, just there are more words in the SimSpell frequency table. Using this, we can then update the SimSpell frequency table using the survey response table in order to get the performance on the right side here. So we have Ebola and ambulance and dying, which is the preferred behavior. This can be further illustrated by looking at the shift in rank of word occurrence between the original SimSpell corpus and our new collection of words, the SMAC survey corpus. I want to highlight on the right that Ebola has been elevated from rank 36,000 to 5, where lower is more frequent usage, and words such as dead, washing, burial, those have also been elevated notably. This all led to much better performance in the spell correction library.
In the digital dataset, there are up to 5 actions that each community is taking to slow the spread of Ebola. We want to discover certain characteristics of the community that lead to certain policies. For example, in chiefdoms where there are more cases of Ebola, are there different policies? What about urban communities versus rural communities? The dataset also includes an action status, which describes if the action is complete, in progress, incomplete, / not achieved, unable to assess progress, or new. We are interested in the incomplete / not achieved policies. What characteristics cause policies to fail? Can we build a predictive model? To proceed, we labeled our policies using active learning. So there's 500 that were hand labeled and then 750 that were labeled by selecting the most informative samples. Using an SEM classifier resulted in a 67% accuracy on a testing sample using this method. The idea with active learning is that it's going to lower the amount of hand-labeled samples that you would need. We're categorized into 11 different groups. We can see that washing hands, reporting sick to authorities / not treating the sick, policies for the dead, and avoiding others are the most common. We can see that there's also some very rare ones like sex, which is avoiding sexual contact. And another clarification we should make is that policies for the dead includes anything with funerals or like caring for dead bodies. So next we did a logistic regression on each of the different types of policies to predict whether or not it would be implemented. And so we saw that rural or urban made a big difference, village side made a big difference, and the severity of Ebola made a big difference by looking at the coefficients that are generated. And so coefficients that are above a 95% confidence interval were common in rural or urban, village size, and the severity, but for authority figures, they were pretty rare. The authority figures include like chiefs, youth leaders, religious leaders, police, and health workers. Now looking at which policies were going to more likely to fail, we began by just looking at which percentage failed. So you can see that health checkpoints are by far the most likely. And to proceed, we then made predictive models. And so the first is very similar to the previous logistic models. It includes all the same dependent variables, and it doesn't include any information about which types of policies they tried to implement. And so that is about 70% accurate. And then if you expand that to include which types of policies they were attempting to implement, it increases the accuracy to 76%. So that's pretty good. This method seems promising to something that can be developed in the future with a data set that was specifically gathered to target this problem. And I believe that with some more work, we could achieve much higher accuracy and potentially save many lives. So just to recap, the size, the urban or rural status, and Ebola deaths are the most influential predictors for which type of policy a community will enact. And predictive models might be able to alert communities that are less likely to follow through with their policies.
So one of the things we were interested in with respect to this data set was investigating how road networks impacted the spread of the disease throughout the country. And to do this, we used a subset of the methods from Strano et al. They used their methods on the whole of Africa. We restricted those methods to only Sierra Leone and used them with respect to the original SMAC dataset. So these methods were primarily comprised of taking a primal representation of the road network, meaning that roads were edges and intersections between roads were vertices, and remapping it to an inverse dual representation where the roads were vertices that shared edges between themselves and other roads with which they had an intersection. So with this latter representation, we were able to discover a degree of modularity in the sense that a road or vertex inside a module was more interconnected with the other roads and vertices inside that same module than it was with roads and vertices in other modules. The basic idea behind a module is that it is roughly representative of a community. And we were interested in communities because we wanted to investigate whether the disease propagated primarily inside of communities before spreading to adjacent communities, or whether it spread to adjacent communities at all. So to investigate that, we also created some spatiotemporal plots. This one on the top left depicts the last reported rate of chiefs in any given chiefdom at any given time. And it is more of a proof of concept than anything else, but it shows which chiefdoms reported data and how the SMAC survey moved throughout Sierra Leone and collected data. The subsequent three plots, the seriously sick male adult, common burial for male adult, and safe burial for male adult on the top right, bottom left, and bottom right respectively, show the rates for those attributes throughout the entire SMAC survey time period. Particularly with the seriously sick male adult, we would hope that we would see the rates for sick individuals propagate to adjacent communities or repeatedly appear within adjacent communities, but overall that does not appear to be the case. We do not see any significant trends where rates of sick individuals, female adult, male adult, female child, male child, any of the above, roughly adhere to communities. So while the original methods used to discover modularized communities may be useful for investigating the overall spread of disease throughout the country, it appears that how the data was collected does not really reflect any trends that we can make conclusions about. That being said, these spatiotemporal plots are still valuable in the sense that they represent the fact that the number of sick individuals often goes down between the first visit from SMAC survey workers and the second visit from SMAC survey workers. Any area that appears red and then subsequently darkens in color or goes straight to black represents a reduction in the overall rate of sick individuals in that specific chiefdom.
2 labeled cases of a non-0% population infected, but with a relatively high population. You can see from the last slides, both of these have over 100,000 people. So these 2 places did pretty well at staving off Ebola. On that subject, here we have surprising chiefdoms, and so these are chiefdoms that have a lot of neighbors with lower percent infections than themselves. So the scale that we're judging here by is actually the percentage of their neighbors that they have a statistically higher percent infection rate than. And you can see a few of these more percent infected regions. And so to help with this, this is just comparing by difference of the standard deviation. And so when we compare by 3 times the standard deviation, we can see the chiefdoms that really truly have a much higher rate of infection than their neighbors. So these could be worth looking at, and it could be interesting to see what they might have done differently from their neighbors. Moving forward, we can see we have kind of an average rate of percent neighbors statistically lower than oneself here, and so we're decreasing the percentage, this average percentage, by neighbors that are higher than oneself, and increasing it by ones that are lower than itself, so we can get a better idea, maybe a better spectrum of what's going on here. And so then lastly, we have the percentage of neighbors that are lower than themselves, and so we can see here some regions that did quite well in staving off Ebola despite being surrounded by high percentage infected regions. Thank you.